Okay. So how many people can solve the quiz? If I ask you again in the second hour, how many people can do it this time? Huh? If I bring exactly the same quiz in the second hour, no change, how many people can do it? Almost like 50. So just to prove that it is not that hard, maybe I can solve it real quick and you can prepare next time. So we have something like this. So this is u of x. So this side of the potential is u is infinity. Actually, let me change the problem a little bit. Let's say here u is equal to 0, and let me say here u is equal to minus v naught. And I'm sending the particle like in this energy, right? So this means, okay, this is so this is u is equal to 0, or like, yeah, this is the 0. So this energy is E, and this energy is E plus V naught. Suppose we are trying to solve this. And in each region, of course, you can write the Schrödinger equation like we did, and then you can look at the sign of the second derivative to determine the kind of solution you need to have. So this one is A e to the minus ikx plus B e to the ikx. So this one is left moving wave, this one is right moving wave. And here k is equal to 2m over h bar squared e. And here, in this region, suppose you started with like exponentials. What will happen is like c times e to the I, this is k prime x, plus d times e to the minus I k prime x. And here k prime is equal to 2m over h bar squared e plus v naught. And now you can say, okay, let me put the boundary condition at x. So here is x is equal to 0. This is x is equal to a. And the boundary condition at x is equal to 0 is going to give this one, c plus d is equal to 0, right? Then d is going to be minus c. Then the wave function here, this wave function is going to be c e to the I k prime x minus e to the minus I k prime x. But this is exactly of the form sine k prime x. But alternatively, I want to start with sines and cosines, because when there is like a box, it's going to be standing wave, and for standing wave, by experience, we like sines and cosines better. So let's also suppose you happen to choose sines and cosines. It's going to be c times sine k prime x plus d times cosine k prime x. When you put x is equal to 0, cosine is 1, but to make the entire wave function 0, d needs to be 0, so this is 0. Okay? And now we need to put the boundary conditions at psi of a continuous. That means c times sine k prime a is equal to a e to the minus I k a plus b e to the I k a. And psi prime is also continuous. And maybe I can just copy. And when I take the derivative, this is going to be cosine, and there will be like a k prime here. And similarly, I'm going to have like minus ik here. And there will be minus here. Now I want to do what I told many of you to do. Just take the ratio side by side. cancel C, cancel this. Sine k prime A over cosine k prime A is 1 over k prime tangent k prime A. And I want to put this ik over here, minus ik. And this is going to be equal to something divided by something else. Yes. Shouldn't be. So it is like this divided by this, and I take this 1 over minus ik to this side. In English, please. I understand what you're saying. Okay. Let's try.
We take a derivative of first one, but we change. Okay.
Yeah. So when I take the derivative, sine became cosine, and there's like k prime. When I take the derivative on this side, minus ik prime came down, right? And I took inside the parentheses of minus ik, and because this was ik, right, I put a minus sign in between. But like, since I know the overall minus sign, like I think if you remember that this is a little bit more advantageous to do the calculation a little bit fast. So the second one is going to be exactly like this, but minus in between. Now I want to collect A's on one side and B's on the other side. So let's do this. So this is going to be A e to the minus I k A times this thing. If you want, there's like a minus here. Minus B e to the I k A. Okay, this is k A times this thing, and I can cancel this minus and make this plus, should be equal to, okay, I need to push this a little bit, should be equal to this denominator, and now I want to collect A's and B's. So this is, let me collect A on the left, A, and you can see there's also e to the minus IKA, which is common. So this is going to be minus 1 minus this thing. Okay, let me fix minus IK is equal to B e to the I KA 1 minus this thing. Then you are asked to calculate B over A. So B over A, let's pull it down a little bit, is equal to e to the minus I K, actually two of these, 2 KA and 1 minus I K over K prime tangent K prime A divided by, and actually there's like, let me put the overall minus here, 1 plus I K over K prime tangent K prime A. So this is part A, you are done. Part B is asking you to calculate the modulus of this thing, like what is the modulus of A? And modulus of minus 1 is 1, modulus of e to the I, anything is 1, and now we are trying to calculate modulus of this. But modulus of a complex number, I x plus I y, if you take the modulus squared, it's going to be square root x squared plus y squared, right? Forget about I, just take the square of x and y, and that's it. And I do exactly this here, 1 plus k squared, k prime squared, tangent squared, k prime A, and divide it by exactly the same thing. Whether it is plus I or minus I, doesn't matter. 1 plus k squared, k prime squared, tangent squared, k prime A. But something divided by itself is 1, as far as I know. So this is 1. And this is a nice thing because it says you have like an infinite wall here, right? Whatever you send should reflect at the end of the day. Of course, some complication may take place, but if you are talking about probability amplitude A being sent, probability amplitude in total A should be returned. But what could be different? The difference could be an overall phase. And in part C, the question is asking you to calculate the phase. If this entire thing is 1, we can write B over A as a phase, and the phase I gave you is like something like this, e to the minus I 2 delta, and this should be equal to this entire thing. This entire thing. But I know this is like a number of unit 1, right? Magnitude 1. Then I can just write this 2 delta is equal to, okay, the minuses cancel.
Hocam, I think denominator should be changed.
So this is plus or minus? Yeah, you can do it yourself later. I think I'm just doing the outline of the calculation. I may have like pluses and minuses wrong here and there, but let me finish this. So this is going to be 2 delta is equal to 2k plus log this entire thing. Some people wrote it like arc, that's also fine, right? Arc function, if you know what arc function is, you can also write it like arc, but like delta happens to be this. And that's the end of the problem. Okay?
We have potential, we have that kind of a solution, and whenever we have...
So this I know from experience, but I think the safest thing for you to do is just write the differential equation. Write the differential equation, look at the sign of the things, and it is always going to be some psi prime is equal to something times psi, and you should ask, is this a positive or negative? And that's the principle. And for example, this one here we have negative, right? This is minus 2m over h bar squared. E is positive, this entire thing positive, total overall is negative, so it is e to the I or e to the minus ik. But if it was positive, it would be decaying solutions. But from this experience, I know it's not going to be decaying solutions, because this problem is going to be like no tunneling. If my energy was like this, I know there wouldn't be like any classical probability here, because energy is the barrier is too high. There could only be these decaying quantum solutions. Then I would just put e to the some kappa x minus e to the, or maybe alpha x, e to the alpha x, or e to the minus alpha x.
So, how were we able to calculate the phase shift by equating the terms to e to the
like this?
to I delta?
So because I calculated the norm and I found the norm to be 1, so this has to be something of the form e to the I alpha, because only things of the form, but I can define things any way I want, so I define the norm like this. I put a minus here, and I put 2 delta. And for applications, this is the phase shift, because of the reflection and scattering, but I don't ask you these questions. I just wanted you to demonstrate technical calculation. It doesn't blow up. These are like sinusoidals, right? These are always going like this. If it was e to the alpha x, it would blow up, right? So these traveling waves are fine. And what the argument was, like, I was like throwing the electrons from like a very far away point, and these electrons were continuously coming to the barrier. And then whatever they do, they return, and my detector collects them afterwards. All right, so if not, I'll continue with hydrogen atom and solutions of Schrödinger equation in the presence of a Coulomb potential. So let me come back here. So just to remind you what we did last time. So we said we are supposed to solve the Schrödinger equation in 3D in the presence of a Coulomb potential. And because of the Coulomb potential, we said it is like more advantageous for us to work in the spherical coordinates. And we wrote the Schrödinger equation in, as usual, only the Laplacian, we wrote it in the spherical coordinates. And then after that, okay, here is the, I think if you don't remember spherical coordinates, these are theta, this is phi. For example, you can calculate z is going to be r cosine theta, x is going to be r sine theta cosine phi, and y is going to be r sine theta sine phi. And after that we said, okay, we expect separable solutions in the sense that there's like a function of r, function of theta, and function of phi. And then we said if we substitute it here, we are hoping that we are going to be able to separate it. And I want to do it today. I thought we did that, but it seems like we didn't. So let's try. So I want to take this Laplacian. And I want to write the equation like this. I want to write it like plus 2. Okay, if you want, in the equation, I am like taking this e to this side. This is minus e plus. So let me do it like this is e minus u, and when I take it back on this side, it is going to be minus e minus u, and this is equal to 0, and this minus is going to cancel this, and it's going to be plus, and I want to write it like 2m over h bar squared. Now I have only Laplacian, right? Because the difficult term is this, I wanted to isolate it in this form. Then this is going to be 2m over h bar squared. I think I had e minus u times psi is equal to 0. And whenever I see psi, I want to write it r r theta phi, and here r theta phi, and here are r theta phi, and also here r theta phi. Okay, so this one, this one, this one, and this one. And we are going to do exactly what we did before. So this derivative is like a r-dependent derivative, and theta and phi functions do not know anything about r derivative, so I can take them out. So this is theta, this is phi, and this entire thing. And I'm going to change this one to r. Similarly, I have only theta derivative here, so I can put r, phi, and this thing. Theta. This thing only knows about phi, so this is, and I'm going to put r and uppercase theta here. And I think lastly I have, okay, let me push this just a little bit. Oh. phi, and I'm going to have 2m over h bar squared e minus u r theta and phi is equal to 0. Good. And I'm going to divide entire equation with r, theta, and phi. This is exactly what we did for like x, y, z Cartesian decoupling. So this is, let me copy that. And if I divide it by like r, theta, and phi, there will only be 1 over r here. There will be 1 over theta here. There will be 1 over phi here, and this one is going to be 1. So that's it.
So
Uh-huh.
you're going to change the side, second to last side to capital phi?
Oh, yes, thank you, good job. So this one is phi, this one is definitely, this one is phi. Yes, thank you. And now I want to multiply this entire equation with r square sine theta, so that I can take this out and isolate this term. So let's also do that. So I'm going to copy. So this r square sine theta is going to go from here. Okay, maybe I can write it here. There is like some r square sine square theta. So and this one is r square sine square theta, and here r square sine square theta. Now, as you can see, I isolated one term, like this term here is only phi dependent. So this thing only phi dependent. So it's like what we did when we find something like this, we called it a constant. And for this case, let me call this minus m squared. Okay. Then del square phi, del phi square is equal to minus m squared phi. So that's the first equation. And now I can put minus m squared phi and continue to like divide the problem. So let me copy this. Take down. So this beast went and happened to be minus m squared. Now I want to separate r and theta from each other. So for this, I am going to divide by sine squared again. So if I divide by sine squared, so this one is going to go, this one is going to go. There will be like a sine squared theta here, and this one is going to go. Good. Now it seems like I have like something r. This is completely, okay, these r's are also gone, which is nice. There's no r, there's no r, there's only r. Okay, it seems like I also separated theta from the r. So it is, let me identify this only theta dependent term. I will, so the first and second is only r dependent. I am going to separate them to their own equation. Okay? So this thing is typically called minus L plus 1. Because I know the result, that's how we define, but if you were doing it for the first time, you could just call it C, that's fine. But to speed up the result, I will call the constant here, and because at some point I'm going to run out of constants to define, so this is going to be then an equation for theta. Let's write it. This equation for theta is going to be is equal to minus L plus 1. Let me modify this equation just a little bit. So this is going to be, I'll take L plus 1 on this side. So this is going to be, okay, let me take it to this side. So this is L plus 1. And this entire thing, now I can delete this. This is plus, and I want to multiply everything with theta. So this is theta is equal to 0. Let me check. 1 over sine dd theta plus L plus 1 minus m squared. Okay, this seems to be correct. So this is my second equation. And like you said, I will now put the r component, this plus this is equal to minus L plus 1. Again, I want to take it on this side. This is going to be plus is equal to 0. And if I multiply, I think I also want to divide by r squared. So this is r squared, r squared, r squared. And now I can take this parenthesis and write it as an equation for r. And this one is gone. And this is my third equation. So let's collect all these equations. Actually, we can see them, right? There is like a theta equation, a phi equation, a theta equation, and r equation. So what we did is like, okay, now these partial derivatives we can change, right? Because there's only one variable for each. So this technically should be d squared, this one also, d, and this one, and all of the derivatives are like full derivatives, no partial derivatives anymore. What we did is we had like a PDE. This is like partial derivative. We had like a one partial derivative, we have one partial differential equation, and we split it into three, and we had three ODEs. We had three ordinary differential equations. Ordinary differential equations are much simpler to solve than partial differential equations. And this is the first important thing. And the second important thing is only R equation depends on U of R. If you go and back, so there is only U in the R equation. In the theta equation, there is no U. And in the phi equation, there is no U. So once you solve phi and theta equations, they are valid for any other potential. So then theta and phi solutions are general. Of course, as long as your potential only depends on R. If you have, like, for example, an anisotropic potential that depends on theta and phi, this is not the case. But generally, we have central potentials, and the form of central potential can change, but they don't depend on angle because of isotropy. Now let's consider the theta equation. So now we can consider we can start thinking about quantum numbers. The simplest is phi equation. And d squared phi, the phi squared plus m squared phi is equal to 0. And what is the solution of this equation? I think everybody knows how to solve this now, right? Second order derivative depends on the function, and there's like an overall constant which is positive. Exactly. So the solutions are phi of theta are some constant time e to the I m phi. And if you go back to the geometry, right? So here is the theta. So if you go wherever you are in the r, theta, and phi plane, if you just do one full rotation and come back, right? You should be exactly at the same point. And that means, so phi of phi should be equal to phi of phi plus 2 pi. Then e to the I m theta is equal to e to the I m theta plus 2 pi, and this tells me m 2 pi is what? Is equal to 0, or like an integer times 2 pi, right? 2 pi times integer, then m is an integer. So that means m should be ... minus 2, minus 1, 0, 1, 2, ... All of them are fine. So we solved the phi equation, but unfortunately we are not as lucky for the theta equation. So for the theta equation, so this is a little bit more difficult. So this is so-called Legendre, associated Legendre polynomials. You can just learn these special functions and see how they work, but for us it doesn't matter. For us what matters is this equation has solutions only. I think we are now familiar that differential equations are only solvable for certain quantized values. And this is also the case only if L is an integer, and so this L is bigger than absolute value of M, right? Because the equation knows about M and L, and this entire differential equation is only solvable if this condition is satisfied. Then we can say they are like solutions, and they can be for L is equal to, I don't know, 0, can be 1, 2, ... all the way up to maybe the other way around. So either I can either like constrain L based on M, or I can constrain M based on L. So I can say L is equal to 0, 1, 2, ... and I can say M is equal to minus L plus 1, ... 0, 1, 2, ... L, right? They are in total minus L to L. They are in total 2L plus 1 different M options. So,
Basically, like, I forgot how you
So we, like, there is nothing, we just defined it, like, because, okay, these differential equations are studied for years, even before quantum theory, and people know when they are solvable and when they are not solvable. To make it clear when they are solvable, they define not some constant c and put like a absurd condition on c. They call it like L plus 1 and put the condition on L. So if you go back and look at the equation, there's no reason for us to call this constant minus L plus 1. So this is a sophisticated case, but this doesn't concern us. Like, as you can see, there are quantum numbers, and these quantum numbers seem to have like nice structure. Choose L, and M is going to be minus L all the way to plus L. There are for 2 L plus 1 different options. And this is like so simple. I think even high school students learn this stuff, right?
Yeah.
Right? Yeah.
Without any reason.
Yeah, but now is the next step, a little bit more than high school. Maybe next year when you are learning quantum mechanics, you are going to see this even in full detail. Actually, if you are taking mathematical methods, at some point you are supposed to solve these things. So there's only one equation left. So here is the R equation. Let me not write, okay, let me take it for you to see. So this equation has solutions, and this one is also very simple, right? So this has solutions if E is quantized and the quantization is given by this minus m e to the 4 32 pi squared epsilon naught squared h bar squared 1 over n squared, and this is minus E1 over n squared, and E1 is equal to, if you put all these constants and calculate, 13.6. So which is nice because this is exactly what you obtain from Bohr model. So in 2 lines you can remember the Bohr model and then find quantized energy values, or you can spend like entire week and solve partial differential equations and find exactly the same energy. So that's actually a very nice thing about physics. So you don't have to, for example, go and do this every time. So and the condition is n can be 1, 2, 3, ... But also n has to be bigger than or equal to L plus 1. And this condition is kind of like this m, right? We first said let's solve m, and m gave a constraint on L, or we said we can put the constraint on m rather than L. Now we can do exactly the same thing. So n is supposed to be bigger than L plus 1, so we can summarize all of these rules as follows. N can be any integer, 1, 2, 3, ... right? L, to satisfy this condition, can be 0, 1, 2, all the way up to n minus 1. And lastly, m can be minus L plus 1, ... 0, 1, okay, minus 1, 0, 1, ... L plus 1. I think how many people know these rules? I think, as far as I know, I think everybody is familiar because they are also asking this in the entrance exams. So you sit down and look at them and you try to remember them. So the psi now is going to be a function of r, theta, and phi, and it is also going to depend on these quantum numbers, right? It's going to be n, L, and m. If you remember the R box, it's exactly like that. For the box, we had these, right? Wave function was dependent on nx, ny, and z. I was technically I should put nx, ny, and nz here. and we have exactly the same thing. They are just a little bit more complicated looking, but that's not a big deal for us, right? And it's going to be R equation. It knows about N and L and R. And uppercase theta knows about L and M. And phi only, okay, let me also put the argument of the function. So this is theta, and this one knows about M and phi.
So the quantum speed number doesn't relate to this topic.
We'll come to that. Right now, we only introduce these numbers. Maybe after the break, I will try to explain how we give meaning to these numbers. What is the physical representation here? And for that, we are going to think about things like this and angular momentum and all those things.